Okay, hello everyone in a new video. So we have reached part 4 of chapter 11, which is the chapter of pressure in liquids and the third unit of mechanics. Then now we are in section number 14 and the title of the section is given by relation between pressure and force. Then previously we have introduced the notion of the pressure, and we have said that the SI unit of the pressure is given by Newton per meter square, and this unit is usually denoted by Pascal. However, referring to this unit, one can notice that it includes a Newton, and the newtons is the unit of the magnitude of the force, knowing that the force is characterized by four properties: the point of application, the line of action, the direction, and the magnitude. The magnitude in the SI is expressed in newtons. So indeed there is a relation between the magnitude of the force and the pressure. Then let's write down the relation between the pressure and the magnitude of the force is given by then the pressure, which is denoted to P, is equal to what? Now let's construct the triangle that includes the pressure and the force. So knowing that the unit of pressure is given by Newton per meter square, then here we can notice that the pressure will be given as the ratio of it's the ratio of the force over a quantity which is expressed in meter square, and we know that meter square is the unit of area. So here at the top we can write that we have F, which represents the magnitude of the force, and the bottom here or here we can say that we have the surface area S. So by referring to the unit, one can construct the formula of P. Then P is given by F divided by S. So the formula of P in terms of F is given by P is equal to F divided by S, and in this case the triangle is given by P, F here, and S at the bottom. So now let me introduce each quantity and its corresponding SI unit. So let's say where P is the pressure, and its SI unit is given by Pascal, which stands for Newton per meter square, in which F represents the magnitude of the force, the magnitude or the value of the applied force, and we know that the SI unit of the magnitude is given by newtons. Moreover, S is the surface area, and its SI unit is given by meter square. Now usually this force is referred to as the pressing force, and this surface area is also referred as the cross-sectional area. Okay, so now we have two formulas for the pressure. So the first one that we have seen previously in parts 1 and 2, which is given by pressure is equal to the density of the liquid times G times H. So usually we use this pressure in order to calculate the atmospheric pressure or the pressure exerted by a certain layer of liquid. However, this formula, we use it usually if we know the magnitude and the surface area. And here let me also say the following note. So here, notice that P and S are neighbors living in the same floor, so they hate each other. In other words, P and S are inversely proportional. Which means that when P increases, S decreases. When P decreases, S increases. So we can say that when P increases, S decreases. Or let me say the following: when S increases, we have that P decreases. When S decreases, P increases. Now, as for the relation between P and F, notice that P and F are neighbors living at different floors, so they love each other. Then we can say that P and S are directly proportional. Sorry, P and F which means that when F increases, P increases as well. And when F decreases, P decreases as well. Now finally we can talk also about the relation between F and S. Notice that F and S are neighbors living at different floors, so they love each other. When S increases, the value of F increases, and vice versa. So let's say that F and S are directly proportional. Which means that when S increases, F increases. When F decreases, S decreases. Sorry, when S here. When S decreases, F decreases. So let's consider the following application. So let me write down here that application number 1. Which is a direct application on the formula P is equal to F divided by S. Then application number 1. Suppose here that the atmospheric pressure, so this is given, that the atmospheric pressure in this case is given by 102 Pascal, 102,000 Pascal. So suppose here we have a container filled with a liquid placed on a table, and let's consider 2 points. So this is the point A at the surface of this, on the free surface of this liquid, and a point B on the bottom of the container, like this. So this is the point B. Now let's say that part 1 of this application is given by give the pressure at A, number 2, calculate the total pressure at B, and in order for us to calculate the total pressure at B, let me give a numerical value for the height corresponding for this layer of liquid. So let's say that this height is given by, for example, h is equal to 30 centimeters. And here let me also say that the density of the liquid is given by 1000 kilogram per meter cube, corresponding for water. And here let me say at the point B, okay. Now number 3, deduce the value of the pressing force F exerted at the bottom of the container given that the cross-sectional area S is equal to 10 centimeters square. So in this case, S represents the surface area, which is the contact area between the table and the container. This is the container, and we here have that S is equal to 10 centimeters square, because we know that the container is being placed at the table, so it's being in contact with the table, and there will be a surface of contact, so we can measure its surface area. So in this case, the surface area is given by 10 centimeters squares. So let's answer these questions. Let's start by number 1. So the given here we have the given the atmospheric pressure and the density of the liquid. So in number 1, they are telling us to give the pressure at A. So notice that in this case, A is at the free surface of this liquid, which is contained in this container. So A is open to the atmosphere, then A will be submitted to the atmospheric pressure. So in this case, this statement is important, and they usually give it half a mark. Now, for this reason, the pressure at the point A is equal to the atmospheric pressure, which is given by 102,000 Pascal. Now, in number 2, calculate the total pressure at B. Since you are interested in the pressure, we consider the point B and we look upward. So above the point B, there is the layer of this liquid. Then the point B will be submitted to the pressure due to this liquid and to the atmospheric pressure that's being applied at the point A and transmitted to the point B according to Pascal's theorem. So here we have that H is equal to 30 centimeters. Knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meters, we divide by 100. Then 30 divided by 100. So this height or depth is given by 0.3 meters. Then the pressure, let's say that B is submitted to the pressure of the liquid. And to the atmospheric pressure. Then the pressure at the point B, since they're asking us about the total pressure, so it's the sum of the pressure due to the liquid, let's denote this pressure by PL, plus the atmospheric pressure, which is given by PA. Now, because PL is the pressure due to a liquid, so it's given by the density of the liquid times G times H. So it is rho L multiplied by G multiplied by H plus the atmospheric pressure, which is PA. Now the density of the liquid is given by 1000. The value of G is given by 10 and the value of H is given by 0.3 in the SI, plus the atmospheric pressure, which is given by 102,000. Now plugging this on the calculator, then it's given by 3000 plus 102,000. Now plugging this on the calculator, then the total pressure at the point B is given by 105,000. So since this is expressed in Pascal, this is expressed in Pascal, the atmospheric pressure, which is the pressure at the point A, and this is in the SI, and we know that the unit of pressure in the SI is given by Pascal, then this quantity will be given by Pascal, expressed in Pascal. So the total pressure at the point B is given by 105,000 Pascal. So here let me say that the total pressure at the point B is given by 105,000 Pascal. Now, as for number 3, they are telling us deduce the value of the pressing force F exerted at the bottom of the container given that S is equal to 10 centimeters squares. So, and by deduce it means that we need to use the previous part. In the previous part, we have determined the value of the pressure at the point B, and notice that the point B corresponds to the bottom of the container. So we know the value of the pressure at the bottom of the container. We are asked to determine the value of the force, knowing also the cross-sectional area. So we know that the pressure and the force and the area are related via the following formula, that P is equal to F divided by S. In this case, no need to construct a triangle for this formula because, we are interested in determining the value of F. So constructing the triangle of this formula, here because we have divide and P will be at the bottom with S and F at the top. We are interested in determining the value of F, so putting our hand over F, then the value of the pressing force exerted at the bottom of the container is given by P multiplied by S. But which pressure? We have two pressures, the pressure at the point A and the pressure at the point B. Since we are interested in determining the value of the pressing force exerted at the bottom of the container, then we are interested in the pressure at the point B. Now we have the value of the pressure B in the SI, which is given by 105,000 Pascal. As for S is given by 10 centimeters square. Knowing that centimeter square is not the SI unit of area, in order to convert from centimeter square to meter square, we simply multiply by 10 to the power minus 4. Then 10 multiplied by 10 to the power minus 4. Then the surface area in the SI is given by 1 times 10 to the power minus 3 meter square. So now the total pressure at the point B is given by 105,000. And the value of S and SI is given by 1 times 10 to the power minus 3. Plugging this on the calculator, then the value of F is given by 105. Since both the pressure and the area are expressed in SI, so the value of F will be in the SI, which is in newtons. So F is equal to 105 newtons. Now, since F, okay, so we have finished this application. Now, let me just mention this as a side remark. So since we have talked about the F as a magnitude, then for sure we can talk about F as a vector. So let's classify this vector, whether it's a contact force or force acting at a distance. Since it's not electric nor magnetic nor weight, so for sure it is a force, is a contact force. And the point of application in this case, we can take it to be the center, which is the point B. Now, as for the line of action and the direction, since it's due to the pressure and it's by its name, it's a pressing force, so it will exert an action downward like this. So it will exert an action at the point B downward like this. So the line of action in this case is given by vertical and the direction is downward. And as for the magnitude, this is the magnitude of this force. And now let's move to the next application, application number 2. So let's consider a solid S. In this case, the solid S is not a cube, it's a rectangular prism placed on a table. Now let's suppose that the solid S has a mass given by 0.3 kilograms. And this experiment is being performed on the surface of Earth. So the value of G is given by 10 newtons per kilogram, which means that each kilogram is being acted by a force of 10 newtons. And let's suppose that the length of this rectangular prism is given by L is equal to, let's say for example, 5 centimeters, and the width of this rectangular prism, which is the solid S, is given by W is equal to 2 centimeters. So we have that the length is equal to 5 centimeters. So this is all given, knowing that centimeters is not a unit of length. In order to convert from centimeters to meters, we simply divide by 100. So 5 divided by 100, then the length is given by 0.05 meters. And the width is given by 2 centimeters. So 2 divided by 100, then the width is given by 0.02 meters. So notice that here the solid S and the table are in contact. And in this case, we can calculate the area of the surface contact, which is the shaded area here, since it represents a rectangle. And we know that the area of the rectangle, which is denoted by S, is given by length times the width. So we can calculate the surface or area, which is the surface of contact between the solid S and the table. Now let's suppose that number 1, calculate the value W of W vector. So here, because the solid S has a mass, then it will be directly subjected to the weight. So number 1, calculate the value W of W. So we need to calculate the magnitude of the W vector. Now number 2, deduce the pressure exerted by, so let's say the pressure exerted at the point A. And let's suppose that the point A is the point of contact between the solid S and the table. So previously, we used to consider this problem as the following. So this is the support or the table. And this is the solid S resting on the table like this. So previously in chapters 8 and 9, we used to consider the problem to be like this. So this is the solid S, and this is the table, and this is the width of the solid S, which is given by, in this case, W is equal to 2 centimeters. Here I cannot represent the length because we are looking at the problem as a front view. So we are looking at the table and the solid in front, from the front, whereas we are looking in this case to the solid and the table in a 3D view. Now the point A in this case is located here, and let's suppose that this is the point G, the center of gravity of S, so the point G will be here, somewhere here. So in this case the weight in this case act vertically downward like this. And notice that the point A is the point of contact between the solid and the table. So we need to answer the following questions. So number 1, calculate the value W of W. So we know the mass, we know G, then W is given by M multiplied by G. The value of M is given by 0.3 and the value of G is given by 10. So this is given by 3 newtons. So what does W represent? It's the force, it's the magnitude of the weight acting on the solid S. Now number 2, they are telling us deduce the pressure exerted at the point A. So let's consider the point A, and since we are interested in the pressure, we look upward. So here if we consider another point, the point B, say for example. Now we know that because the point B is open to the atmosphere, then B will be directly submitted to the atmospheric pressure. However, as for the point A, okay, we are interested in the pressure, so we look upward. Then A will be submitted to the pressure of this solid. However, it's not submitted to the pressure of the atmosphere because of the following reason. So notice that what is separating the points A and B is solid. And Pascal's theorem states that only liquids transmit pressure. Now because this is a solid, then the atmospheric pressure will be not transmitted to the point A. So A will be only submitted to the pressure of the solid. So let's say that A is submitted to the pressure of the solid. Solid S, let's say for example. So in this case this statement is important and they give it half a mark. So now we need to calculate the pressure. We know that there exists 2 formulas in order to calculate the pressure, which is given by pressure is equal to the density of the liquid times G times H, or the pressure is given by the magnitude of the pressing force divided by the cross-sectional area, in which S represents the surface of contact between the 2 bodies that are at interaction. Now we cannot use this because for the following reason, that we don't have any liquid. So we are left with this. Then for sure we need to use the following formula, that P is equal to F divided by S. But in this case, what is F that we want to use in order to calculate the pressure? So notice that here the solid S is being acted by the force of gravity. So let me draw it here, which is the weight acting vertically downward. So as you can notice that the weight is the force that causes the solid to be in contact with the table. So we can say that the weight is the force that causes the pressure on the table. So here what does F represent? F represents the magnitude of the weight vector W. So F represents W. So we can say that P is given by W divided by S, because F is equal to W. Now we know that the value of W is given by 3 newtons. In order to determine the value of P, it's left to determine the value of S. Now here, because the surface area here represents a rectangle, so we can calculate S using that S is equal to length times width. Now the value of the length in the SI is given by 0.05 and the value of the width is given by 0.02. Plugging this on the calculator, then the cross-sectional area or the surface area in contact is given by 1 times 10 to the power minus 3. Since the length and the width are expressed in meters separately, so S will be in meters square, which is the SI. So now after we have determined the value of S and the SI, So 3 divided by 1 times 10 to the power minus 3. Then the value of P is given by 3000. Since both F and S are expressed in the SI, so the value of P will be in the SI, which is in Newton per meter square. And this unit is usually denoted by Pascal. And now let's move to the next section, which is an application on Pascal's theorem. The title of this section is given by the hydraulic press. Then section number 15, hydraulic press. Statement number 1. What is the hydraulic press? The hydraulic press is a machine that is used. Okay, so it is a machine used to lift heavy objects The functioning of the hydraulic press is based on Pascal's theorem. Statement number 3. So the heavy object is placed on the surface of larger value So this document on the right shows the hydraulic press. It consists of 2 branches. So this is branch number 1 and this is branch number 2. Now these 2 branches are closed by pistons. So this is piston number 1 and this is piston number 2. And the two branches are connected via liquid L. Now notice that this branch has a cross-sectional area S1 and branch number 2 has a cross-sectional area S2. So as we can notice that S2 is greater than S1. So a force F1 is being applied to the branch 1 of the cross-sectional area S1. So we obtain a force F2 on the cross-sectional area S2. So here at this branch we can define the pressure P1. And at the branch 2 we can define a pressure P2. So according to Pascal's theorem, liquids transmit pressure. So the pressure that is exerted on branch 1 will be transmitted to the pressure 2. And according to Pascal's theorem, we have that the pressure at the point 1 is equal to the pressure at the point 2, since liquid transmit pressure in all directions. So according to Pascal's theorem, we have that pressure at point 1 corresponding for the branch 1 is equal to the pressure at the point 2 corresponding for the pressure 2, but we know that the pressure is related to the force and it's given by the ratio of the force over the cross-sectional area. Then we can say that here that F1 divided by S1, so we have replaced P1 by F1 divided by S1, and we will replace P2 by F2 divided by S2. Usually the heavy objects are placed on branch 2. And now let's solve the following exercise as a direct application on the hydraulic press. So exercise 10. A hydraulic jack is used to lift cars. Document 1 shows the principle on which it works. Suppose that a downward force of magnitude F is equal to 1 newtons. So the value of F1 is given by 1 newtons. Acts on a piston of area A1 is equal to 0.01 meters square. Let me write here that the magnitude of F1. So here F1 is being represented by this vector. So it acts vertically downward, having a magnitude of 1 newtons. So it acts on this piston, having a cross-sectional area given by A1 is equal to 0.01 meters square. So everything here is in the SI. The other area of the other piston is A2 is equal to 0.5 meters square. So here in this figure, they are showing the hydraulic jack, and in document 1, they are showing a principle on which this hydraulic jack works. Now, number 1, state Pascal's theorem. So Pascal's theorem is given by liquids transmit wholly. Transmits, let's say transmit wholly and in all directions. The variations of pressure to which they are submitted. And now in number 2, calculate the variation of pressure transmitted through the liquid. So this is the liquid. We need to calculate the variation of pressure. So for example, if you consider the other piston, which is denoted by 2, let's denote this piston by 2 and this piston by 1. So the hydraulic jack consists of 2 pistons that are connected to each other via liquid. Now we need to determine the value of P, and we have F and A. So pressure, we know that pressure, force and area are related via the following formula. Pressure is equal to force divided by area. Here F represents the magnitude or the value of F vector. Now here in this case we don't know the magnitude of F2, but however if we consider the first piston, we know the magnitude of the force vector F1 and we know the cross-sectional area. So here the force is denoted by F1 and the area is denoted by A1, so let's use the same notation. So and let's denote this pressure by P1 because everything carries the index 1. Now the value of F1 is given by 1 and the value of A1 is given by 0.01. Now plugging this fraction on the calculator, then the value of P1 is given by 100. Since both F1 and A1 are expressed in the SI, so the value of P1 will be expressed in the SI, which is given by Newton per meter square, and pressure is usually denoted by Pascal. So the variation of pressure transmitted through the liquid is given by 100 Pascal. Now in number 3, determine the magnitude F2 of the force F2 acting on the other piston due to this variation. Here let me write that P1 So P1 is equal to 100 Pascal. Now determine the magnitude F2 of the force F2 acting on the other piston due to this variation. So also F2 can be determined from the following relation, that the pressure is equal to force divided by area, knowing that we are interested in determining the value of the force. So constructing the triangle of this formula, since here we have divide and P will be at the bottom, F at the top as here. So the value of F, putting our hand over F, so it's given by P multiplied by S. We are interested in determining the value of F2, which is equal to the pressure at the piston 2 multiplied by the cross-sectional area of the piston 2, which is given by A2. Now we have the value of A2, which is given by 0.5 meters squared. Now in order to determine the value of F2, we need to know the value of P2. However, here, if you notice that in number 1 they have asked us to state Pascal's theorem, and we know the value of P1. Now according to Pascal's theorem, liquids transmit wholly and in all direction the variation of pressure to which they are submitted. So the variation of pressure, which is P1 submitted at the piston 1, will be transmitted to the piston 2 having a cross-sectional area A2. So here let's say, according to Pascal's theorem, so always in physics we need to mention the theorem that we are using, so they give it half a mark. We have that P1 is equal to P2, but we know that the value of P1 is given by 100 Pascal. Then the value of P2 is given by also 100 Pascal. Now after we have determined the value of P2, now we are ready to determine the value of F2. P2 is given by 100 and the value of A2 is given by 0.5. Plugging this on the calculator, then the value of F2 is given by 50. Since both P2 and A2 are expressed in the SI, so the value of F2 will be expressed in the SI, which is in newtons. So the magnitude of the pressing force exerted by the piston on the cross-sectional area A2 is given by 50 newtons. So here notice that F1 is being exerted on the piston and F2 is being exerted by the piston. Now section number 17, instruments that are related to pressure and densities. So let's start by this instrument. So this instrument is known as the densimeter. So notice that its name is given by densimeter. Densi stands for density and meter, which means it is an instrument. And indeed it is an instrument that measures the density of a liquid. So let's say it is an instrument. Used to measure the density of a liquid. Now what about the pressure? So in this case, this is a sketch of the functioning of the manometric gauge. So let's write down the second instrument is given by the manometric gauge. Is an instrument that detects pressure variation, then this instrument can measure the difference in pressure variation. Now as for the final instrument, so this instrument is given by the barometer. Now meter, it means it is an instrument, and baro, so bar is unit of pressure, so is an instrument. That measures the pressure. And now let's move to the next section, which is an exercise. Okay, exercise number 10. Consider a rectangular block of mass m is equal to 5 kilograms. So the mass is given in the SI. Having the dimensions 2 centimeters, 5 centimeters, 10 centimeters. So because it is a rectangular block, so these dimensions allows us to calculate the volume or the surfaces area, the three surfaces area of this rectangular block. So let's denote this by the length, and this by the width, and this by the height. So it's not important which dimension is given by the length and the width and the height. So let's say that the length is given by 2 centimeters, knowing that centimeters is not a unit of length. In order to convert from centimeters to meters, we divide by 100. Then the length is given by 2 divided by 100, which is equal to 0.02 meters. So this is 0.02 meters. And the width is given by 5 centimeters, which is equal to 5 divided by 100. And the height is given by 10 centimeters. From centimeters to meters, we divide by 100. So the height is given by 0.1 meters in the SI, and take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Number 1, equilibrium of the block. We place the block on the surface of a horizontal glass table. So let me here do a small sketch. So suppose that this is the table, and this is the block. Now we place the block on the surface, so it is in equilibrium. Then in this exercise we can use the condition of equilibrium at any moment. Now 1.1, name the two forces acting on the block. So because this block has a mass which is given by 5 kilograms, then it will be directly subjected to the weight. So the first force is given by the weight W. So we expect that this block must fall, but it is at rest and at equilibrium on the table. Here, because we have a support, so the other force will be the reaction of the support, or let's say the normal reaction N. And now in 1.2, give the relation between these forces that characterizes the condition of equilibrium. So they are asking us about the condition of equilibrium. We always start by the title at equilibrium. Always on the left we write the sum of forces acting on the rectangular block, and they are given by the weight and the normal reaction. And on the other side of this equation, we will write a zero vector corresponding for the condition of equilibrium. Now moving the n vector to the right hand side, we have that w vector is equal to minus n vector. So what does the first equation tells us? That both forces acting on the rectangular block cancel each other in order to give us the zero vector, whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Now in 1.3, for each of these of the two forces, specify the line of action, the direction, and calculate its value. And here by the value they mean the magnitude. So let's start by the properties. Okay, by the line of action, the direction, and the magnitude for the weight, they are not asking us about the point of application. And we will list these properties according to the Prism order. So we'll start by the line of action. So the line of action of this force is given by always vertical, and the direction is given by downward. Notice that I didn't list the point of application because we are not listing all the properties, we are just listing the line of action, the direction, and the value. The value corresponds for the magnitude. Now the magnitude, so notice that here we have the mass and we have the value of g. Then the magnitude of w can be calculated using, so notice that I didn't place a vector for the w because it is the magnitude, and whenever we have the magnitude we drop down the vector. So w is equal to m multiplied by g. The value of m is given by 5 and the value of g is given by 10. Plugging this on the calculator, then the magnitude is given by 50. Since both m and g are expressed in the SI, so the value of w will be in the SI, which is in newtons. So the magnitude of the weight is given by 50 newtons, and this is important. And now let me list here the properties of the normal reaction. Okay. So notice that this sketch is not yet a part of the answer. As for the line of action, we know that because according to this relation, so they have the same line of action which is vertical and opposite direction. Since w has a direction which is downward, and the normal reaction has a direction which is upward. So the line of action is vertical, and the direction is upward, opposite to that of the weight. And we can verify this by referring to this figure. So this is the table, and we know that always the normal reaction is perpendicular to the support. So this is perpendicular to the support like this, and as we can notice that the line of action is vertical and the direction is upward. As for the magnitude, so we don't have any explicit formula in order to calculate the value of the normal. However, according to this relation, so let's say that w vector is equal to minus n vector, or let me complete this part here. Okay, so let me say that in magnitude, so now in magnitude we drop down the vectors and we remove the minus sign, so w is equal to n, but we know that the magnitude of w is given by 50 newtons. Then the magnitude of the normal reaction in this case is given by 50 newtons as well. So here the magnitude of the normal reaction is given by 50 newtons, since the rectangular block is at equilibrium, which means that both forces acting on the rectangular block are equal in magnitude. So let me make some space here. Now in 1.4, draw a sketch. Okay, so this is the sketch. Using a scale of 1 centimeter for 25 newtons to represent these forces, and by represent it means that we need to draw these forces. Okay, so in order to draw these forces, we need to determine the length of each vector, and this can be done using the scale. So knowing that the scale is a connection between the length of the between centimeters and the newtons, which allows us to draw these factors. So 1 centimeter corresponding for 25 newtons, because our rulers are graduated by centimeters and not by newtons. So now we know that the magnitude of each force is given by 50 newtons, and this value correspond to 1 multiplied by 50 divided by 25 correspond to 2 centimeters. So the length of each vector acting on the rectangular block is given by 2 centimeters. Now, in order to draw these factors, we need to take into consideration the building properties. We know that because the weight is classified as an action at a distance, then the point of application will be the center of gravity G of the rectangular block. Whereas for the normal reaction, since it's a contact force, then the point of application will be the point of contact between the rectangular block and the table. So this is the point. And now let's represent these forces. We know that the weight acts vertically downward, and the length of the weight is given by 2 centimeters. So this is the weight W of length 2 centimeter corresponding for 50 newtons according to this scale, whereas for the normal reaction it acts at the point A vertically upward like this. So this is the normal. Let me resize this block. So the name of this vector is an vector of length 2 centimeters, worth of magnitude 50 newtons. Now part 2 of this exercise, pressure exerted by the block. The block is placed successively and independently on the same glass table on each of its 3 faces, S1, S2 and S3. And now here let me do a small sketch in order to explain what's happening. So this is a front view of the experiment. Now if you consider the table in 3D, this is the table. So now the rectangular prism in 3D is given by, say for example, like this. Now as you can notice that this rectangular prism has 3 faces. So this is the face S1, let's say. This is the face S2, and this is the face S3. Now it also has other 3 faces. So it has another face facing S1, and another face symmetric or facing S3, and another face given by S2, which is now in contact with the glass table. This is the glass table. Now here in this case they are giving us the dimensions of each of these faces. So face S1 has dimensions 2 centimeters and 5 centimeters. So in this case it's being placed on the face given by the dimension, the length and the width. And as for the face S2 is given by 2 centimeters corresponding for the length, 10 centimeters corresponding for the height, and the face S3 is given by the width and the height. Now in 2.1, so now knowing the dimensions of each face, we can calculate the area of S1, the area of S2 and the area of S3. In 2.1, calculate the pressure exerted by the block on the glass table in each of its 3 positions. And this is important, 3 positions. Now here the rectangular block is being placed on the table, but we don't know in which phase. So here we have three possibilities which one can place this rectangular block. So the first possibility is on the face S1, the second is on the face S2, and the third one is given by on the face S3. In each of the following positions, they are mentioning the three positions, we can determine the pressure. Why the pressure is different in these three positions? Because here we need to calculate the pressure. We know that the pressure can be calculated using two methods, either from the density of the liquid times G times H, or from P is equal to F divided by S. So here, because we don't have any liquid, we will not use this method and we are left with this. So in the first part of this exercise, we have determined the magnitude of the force. So the two forces, the normal and the weight. Now I will explain which force we will use. Now, because this pressure depends explicitly on the surface area, so for each surface area, the value of P will change. So we have three pressures and they are given by P1, P2, P3, corresponding for the faces S1, S2, and S3. Now it's left to identify which force we need to use. So we will use the weight. Why? Because it is the one that is exerting an action on the rectangular block, and it's pushing it, pulling it downward toward the glass table. So it is the one that is causing the pressure at the point A. Now notice that also the normal reaction exerts pressure at the point A, but this normal reaction is exerting an action vertically upward, whereas the weight is exerting an action vertically downward. However, if we use both the weight and or the normal, both answers are considered to be correct since they are of same magnitude. So let's start by calculating the pressure P1 corresponding for the face S1 of S1. So the pressure P1 is given by the force divided by S1. So in this case, the force is given by the magnitude of the weight divided by S1. So in this case, no need to construct a triangle for this formula because this is the quantity that we want to calculate. Now we know the magnitude of the weight to be 50 newtons. It's left to determine the surface area S1. So notice that the surface area S1 is considered to be a rectangle. So what are the dimensions of S1? S1 is given by 2 centimeters and 5 centimeters. So let's say that this is the 2 centimeters. And this is 5 centimeters. So I have chosen this side to be 2 centimeters because it is in common with S2, and notice that S2 has another dimension which is given by 2 centimeters. So this is the common. So here actually the drawing is not important. What's important, the calculation. So now let's calculate. So don't get confused with this. Let me erase it. So I will not place the dimensions on the figure. So this is S1. Now let's get back to P1. In order to calculate P1, we need to determine the value of S1. So the area S1 is given by the length times the width. Now the length in the SI is given by 0.02 multiplied by the which is given by 0.05. Now plugging this on the calculator, then the value S1 is given by 1 times 10 to the power minus 3. Since the length and the width are expressed in the SI, which is meter and meter, then the value of S1 will be expressed in the SI, which is given by meter square. Now in this case, 50 divided by 1 times 10 to the power minus 3, then the value of the pressure is given by 50,000. Since both F and S1 are expressed in the SI, so the value of P1 will be in the SI, which is Newton per meter square, and this unit is usually denoted by Pascal. So the value of the pressure exerted on the table when the rectangular block is placed on the surface area S1 is given by P1 is equal to 50,000 Pascal. Now as for the pressure P2 corresponding for the face S2, Similarly, P2 is given by F divided by S2. So it's equal to the weight divided by S2. Now the value of the weight is given by 50. It's left to determine the value of S2 corresponding for the face given by the length and the height. The value of the length in the SI is given by 0.02. And the value of the height is given by 0.1. Now plugging this on the calculator, then the value of S2 is given by 2 times 10 to the power minus 3. Since both the length and the width are in meters, then the value of S2 will be expressed in the SI, which is meter square. Now replacing the value of S2 in this relation, then the value of the pressure P2 exerted on the glass table when the rectangular block is being placed on the surface area S2 is given by 25,000 Newton per meter square. Everything is expressed in the SI, and this unit is usually denoted by Pascal. Then P2 is given by 25,000 Pascal. So as you can notice that for each position, the value of the pressure changes, but what's remaining constant is the magnitude of the force applied on the table. Now finally, as for the pressure P3, let me write it here. We are still in part 2.1. Corresponding for the relation F divided by S3, which is given by weight divided by S3. Now the dimensions of S3 are given by the width and the height, corresponding for 0.05 multiplied by the height, which is given by 0.1. Now in this case, the rectangular block is being placed on this face. Previously it was placed on S2, and in the beginning it was placed on S1. Now plugging this on the calculator, then the value of S3 is given by 5 times 10 to the power minus 3 in the SI meter square. Replacing this in this relation, so 50 divided by 5 times 10 to the power minus 3. Then the value of P3 is given by 10,000 Newton per meter square, and this unit is usually denoted by Pascal. So the value of the pressure P3 is given by 10,000 Pascal. Now finally in part 2.2, knowing that the glass table breaks when the pressure exerted by the block on it exceeds 20,000 Pascal. So in this case, the glass table breaks when the pressure exerted on this table exceeds 20,000 Pascal. On which face should the block be placed on the glass table in order to avoid the risk of breaking it to justify your answer? So notice that here in this case, the rectangular block can be placed on a glass table in 3 different positions. Actually they are given by 6, but why we are reducing them into 3? Notice that because this rectangular block, for each face, it has another identical face. For this reason, the 6 faces of the rectangular block in the 3 dimensions are reduced to 3. So indeed, the different positions that are of our interest are given by 3 and not by 6. So, and they are given by the face S1, S2, and S3. According to these positions, the solid S will exert pressure on the glass table, and they are given by the pressure P1, P2, and P3. So this glass table breaks whenever the pressure exceeds 20,000 Pascal. So these are the values of the pressure. So we have 50,000, 25,000, 10,000 Pascal. So the only pressure which is less than 20,000 Pascal is given by 10,000 Pascal, and 25,000 Pascal P2 is greater than the pressure, which is 20,000, the same for P1. Then the only pressure which is less than 20,000 Pascal is given by P3. This pressure P3 corresponds for the face S3. So they are asking us on which face should the block be placed on the glass table. So this face is given by P3. So now let's explain. Since the pressure P3 corresponding for S3 is less than 20,000 Pascal. So between the brackets 10,000 Pascal is less than 20,000 Pascal. Then the rectangular block must be placed on the face S3 in order to avoid the risk of breaking. And by this we have finished solving this exercise. So that's it for me in this video, guys. In the next part 5, we'll complete solving exercises on this chapter.